to try to now take a look at the phase portrait for this system. We've determined that it's Hamiltonian. We've determined that its Hamiltonian function is sine of xy. So I know that the level curves for sine of xy, so that's just sine of xy equaling k for some constant k, those are going to be my solutions to this system. So I'm just going to pick some strategic values for k and start to see what that looks like. Let's start with k equals 0. So if k is 0, then I know that sine of x times y has to equal 0. But that means xy would have to be some multiple of pi. So n times pi, where n is an integer. This just says n is an element, z is the set of all integers. Okay. So let's take a look. N could be 0, in which case I would have x times y equals 0. That's kind of a special case because that would mean that x equals 0 or y equals 0. So that tells me that my axes, x is 0 would be the y-axis, y is 0 would be the x-axis. Those are actually solution curves. Okay. Now, I don't know whether the entire line is one solution curve or whether it's broken up and this section is a curve and that section is a curve. We'll get there, okay? But the axes are solution curves. Okay. Now, if n happened to be 1, then x times y would be pi. Now, what's nice about having a positive number there is I know that neither x nor y is 0, so I can go ahead and solve for y. Y is pi over x, which is just pi, times 1 over x. Okay. Now, that's just a multiple of my reciprocal function. I know what the reciprocal function looks like. I'm just scaling it by a factor of pi. So instead of going through the point 1, 1, it's going to go through the point 1 pi. That just skews it a little bit. Instead of negative 1, it'll be negative 1, negative pi. Again, that just skews it a little bit. Okay. So this curve right here actually corresponds to xy equals pi. I'm labeling that because that's going to help me out a little bit later on to have that. If I let n equal 2 so that I got xy equals 2 pi, I'd just be scaling by a factor of 2 pi. So all that's going to do is stretch it a little bit higher up. So this would be x times y equals 2 pi, and here it would be a little bit lower down. Now, pi and 2 pi are not the values of k. K for all of these curves is just 0. So if I'm on this curve, and I move along this curve, and I say, what's the value of h? It's always going to be 0 here. I'm just recording the value of xy that gets me there because that's going to help me out in a little bit. So far, we looked at what happens if n is 0 or if n is positive. And I can sort of see if n is 3 or 4 or 5, I'm just going to keep getting curves just that are further and further away. Let's look at if it's negative. If xy is equal to negative pi, y is just negative pi times 1 over x. All that's going to do is give me a mirror image of stuff in quadrants 2 and 4. Negative 2 pi would just give me one that's further away from the origin. So I'm just going to label here xy is negative pi, xy is negative 2 pi. Okay, excellent. I'm liking it. Let's take a look at some other values for k. I'm thinking we want to take a look at what if k is 1. That's the biggest that sine can be. So if I look at sine of xy equaling 1, well, that would mean that xy would be pi over 2 plus an integer multiple of 2 pi. So again, where n is an integer. If I just take a look at x times y equals pi over 2, adding nothing to it, I'm going to get y equals pi over 2 times 1 over x. So it's also just a multiple of the reciprocal function. Okay. Now, these curves here corresponded to x times y being 0. This corresponded to x times y equaling pi, and so I got y was pi over x. Pi over 2 is between 0 and pi, so I'm going to have a curve that looks something like so. Okay. So for the green curve, let's see. For the green curve, I've got x times y equals pi over 2. And I'm just going to make a note that that means the value that we're getting here is 1. So this was x times y equals pi over 2. I guess I don't really need to make a note of that. I know sine of pi over 2 is 1. Okay, excellent. Now, the next value I would get that's positive would be x times y equaling 5 pi over 2. That would be y equals 5 pi over 2 times 1 over x. So it's a multiple of my reciprocal function. But notice, 5 pi over 2 is bigger than 2 pi. So if this curve was x equals 2 pi, sorry, xy equals 2 pi, 5 pi over 2 is going to be above that. So that's xy equals 5 pi over 2. Okay. So you'll notice I've got these two consecutive level curves for 0 where I won't have a green curve in between. That's because sine goes from 0 to 1 to 0. In between these two zeros, I'm going to have a low value of -1, then back to 0, then to 1. So I can sort of see the pattern that I'm getting here. So over here, I will have another level curve there. Okay. Now, if I were to take a look at negative values of that. So if I take a look at xy equals -3 pi over 2. Okay. So that would be subtracting 2 pi from pi over 2. I'm going to get that y is -3 pi over 2 times 1 over x. Again, it's just a multiple of 1 over x, but notice that -3 pi over 2 would be between -pi and -2 pi. So I'm going to have that curve in between these two blue ones, and down here in between these two blue ones. Okay, looking good. Let's take a look at what we get for if k is equal to -1. So sine of xy would equal -1. Okay. So that's going to mean that x times y is going to be 3 pi over 2 plus 2 pi n. Okay. So if I look at x times y equals 3 pi over 2, that's y equals 3 pi over 2 times 1 over x. Okay. And let's see, this was what we had for pi, and this was 2 pi. So just as predicted, that curve is going to be in between these two blue ones. Okay. So essentially, in between successive blue curves, which is where sine of xy is equal to 0, we're either going to have one of these green curves, which is where sine is equal to 1, or one of these pink curves, which is where sine is equal to -1. Okay, I'm liking this. So let's now take a look and see if we can find our equilibrium solutions and then the orientations for the curves. Okay. I want to check for equilibrium solutions, because if I have any equilibrium solutions, those might divide some of these curves up into places where the orientation might be different. Okay. So if I take a look at equilibrium solutions, that means that I want x prime to equal 0 and y prime to equal 0. Okay. Now an easy way to do that is to just make x and y both 0. Okay. Because that'll kill off both of them. So 0, 0 is an equilibrium solution. Okay. If x isn't 0, then cosine of xy has to be 0. And if cosine of xy is 0, then I'm at an equilibrium point. So anytime cosine of xy equals 0, I'm at an equilibrium point. But notice, cosine is 0 precisely when sine is either 1 or -1. So all of these pink and green curves, so the green curves were where sine was 1, and the pink curves were where sine was -1, all of those are actually, whoops, I left one out here too. All of those are actually equilibrium points. So this isn't one solution curve. This is infinitely many individual points, each of which is an equilibrium solution. And that's true for every single pink and green curve that I have. Those all consist of equilibrium solutions, and then I've got this equilibrium solution right here. Let's take a look at the orientation of our other solutions. So now I can see that the x-axis isn't just one solution curve, it's actually three. I've got the left side, I've got the equilibrium point at the origin, and then I've got the right side. So let's get the orientation along there. Okay. So over here, y is 0, x is negative. Okay. So if I take a look, y being 0 kills off y prime. That makes sense because I can see I've got to be going either left or right if I'm staying on that horizontal line. Y being 0 also makes x times y 0. Cosine of 0 is 1. If x is negative, x prime will be negative. So we will be going to the left over here. On the other hand, over here, x is positive. So x prime is going to be a positive number times 1. So we'll be moving to the right.